Hello everyone and welcome to the Machine Learning Meetup. We're going to make a start. Well, as people start to filter through, I'll just give some quick introductions. So today we have Nick Cheney from the University of Vermont, who's going to be talking to us with a talk entitled Learning to Continually Learn. We will then have a Q&A. So the talk will be 40 minutes, then we'll have a 20-minute Q&A session, which will be facilitated by Brandon Amos from Facebook AI Research. The only thing that you guys need to remember is that we would like you to start filling up the Q&A during the talk. So don't wait till the end of the talk for the Q&A for you to be putting your questions into the Q&A. Q&A buttons at the bottom of the screen. You can chat to the panelists if you want, if you have any questions. And what else is there? Oh, if you want to ask your question yourself, you can put your hand up and we'll call for you and we'll unmute you so you can ask your question yourself. We'd really prefer people to ask the questions themselves if they can, rather than us reading it out, because it makes for a better discussion. So yeah, do put your hand up and we will ask you to ask your question out. We're going to favor people who put their hands up to ask their questions. Great, I think that's everything from me. So I'm going to hand over to Nick. Thanks, Nick.
Great, hi everyone. Thanks so much for having me. It's a great pleasure to be here. And thanks to all of you for taking time out of your evenings. I hope this will be fun and really interactive. So again, please ask questions and raise your hand whenever you want to throughout this talk. And I'll try and make sure to leave time at the very end too. So I'm Nick Cheney, assistant professor of computer science at the University of Vermont. And as Martin mentioned, I'll be talking about a recent paper we just put out called Learning to Continually Learn. This is on arXiv currently and will be in proceedings next month at the European Conference of Artificial Intelligence. So first of all, I want to say a huge thanks to a fantastic group of co-authors and collaborators. I could say great things about all of these people, but especially want to call out the lead author, my PhD student, Sean Bolio, as well as my co-senior author, longtime collaborator and friend, Jeff Clune, who's at OpenAI Research right now. So to start us off with a very ambitious and lofty goal, I want to talk about artificial general intelligence. Not too much in depth, but just to say that this is a very lofty goal to have human level intelligence in machines. And we can think of lots of advantages, but of course there's also lots of challenges. And the one that I'm going to particularly focus on today is the type of data and the type of experiences that we as humans and agents in the world face that's very different from the way we traditionally train machine learning systems. So in particular, we see lots of data kind of bombarding us all of the time throughout our experience. Some of that is really highly correlated in time that, what I'm seeing right now is very closely related to what I just saw or what I might see in my office tomorrow. But that said, it might be very different from what I see, this weekend or 10 years from now as we have a drift of inputs over time. And this is very much at odds with the traditional way that we think about machine learning, of having some oracle knowledge of all of the data that we might expect to ever see, which assumes a very stationary distribution. And that if we can just shuffle this data and train a model on it, then we can really just learn during this training phase and statically deploy the model out in the real world. So this would be fantastic if this was the way that the real world worked, that it never changed over time. But of course, we know that circumstances, that context, that experiences are maybe highly correlated locally, but change quite a bit over our lifetimes. So really the way I want to frame this is continual learning, which is to say we see sequences of inputs over time, and especially I'm going to say a sequence of tasks over time. the tasks that we see, we can think of training a model on each of those in a sequence, in an online or in a continual manner. And we can think about lots of metrics that we care about with these types of data streams. So for example, we could care about how well we do on the most recent thing that we've seen. This is pretty common in transfer learning. It's really the end of the line that we really care about. In more lifelong learning, and certainly the way that we as humans experience the world and learn things, what we care about is likely not just what we've most recently seen, but being able to understand and act on all of the experiences that we've had throughout our lifetime. And in particular, the metric that we're going to focus on here is really just the ability at the end of this entire sequence, assuming some finite sequence of tasks or images, how will we do at retaining knowledge on held out examples of all of those tasks that we've seen over our lifetime. So for any of you who've worked with this problem, or really any machine learning system in deployment, of course you know that what I've laid out is really a big challenge. That what we see, especially in neural network models, is if we present one task, our model will fit its parameters to that one task very well. But as soon as we introduce a new task without interleaving examples of things that we've seen before, much of that network is overwritten with our new knowledge or new skills. And this concept we refer to as catastrophic forgetting. And this will be the main thing that we try to address in this talk. So obviously this is very different from the way that humans experience and learn in the world. Things that we've learned long ago are, as we say, as easy as riding a bike. Just like riding a bike, where we've maybe not done these things for a very long period of time, and maybe we've learned lots of other skills since we've last ridden a bike. That maybe we learned how to play chess or spike a volleyball or cook gnocchi. But once we get back on the bike, we still remember how to do it. We don't accidentally get confused and start trying to play chess while we're on our bike, which sounds comical, but is really the way that catastrophic forgetting and overwriting happens in most neural networks, is that we have a very strong recency bias towards the things that we've most recently been trained on. So this is a widespread problem throughout online continual learning, and so lots of very smart and creative people have tried approaches to solving this. At the most naive, we can think of just putting penalties on how much we allow weights to move as we learn new tasks. This is helpful in some circumstances, but you can obviously imagine scenarios where preventing the network from learning not only doesn't maintain performance on our old tasks, but allows us or doesn't allow us to learn the new thing that we care about. There are much more clever approaches. For example, if we have labels for each of our tasks and know when they start and stop, and actually even know what the loss functions are for those, there are lots of heuristic metrics to change weights that are important for one task when you're in that task, but preserve the ones that are important for other tasks that you're not currently in at the moment as well. And EWC is a great example of that, but there's lots of others which all use slightly different approaches or slightly different heuristics, like synaptic intelligence, learning without forgetting. The list goes on, and all of these are really fantastic works, and I think are very interesting, and certainly don't want to downplay the importance. But I'll just say that there's another approach that I think is equally interesting and should be explored certainly in parallel. So this is the idea that instead of imagining all of the particular strategies and building blocks that we might want to incorporate into our systems, what we want to do is find out what the thing is that we ultimately care about and use machine learning to figure out how to find strategies that do well at that task. So in our case of catastrophic forgetting, we want to be very explicitly asking the systems to learn without forgetting. So this follows a trend that we've seen in the field for a very long time. And really it is the field itself, which is to take features that might have been hand designed and to use machine learning to try and automate how we search for them. Obviously, we can think of lots of heuristics within convolutional neural networks that even as simple as looking for filters that light up similar things to the brain, or specific strategies or loss functions, like thinking that sparse representations are important for mitigating forgetting. We've seen that automating this approach, we find features, visual features in this case, that are as or more effective than the hand-designed ones. And this automating of the search process comes at the cost of compute and data, but has huge savings in human time and in deep thought. With the abundance of compute and data, I think that more and more will be faced with the scarcity of human time, and I think that these approaches will become more and more appealing moving forward. So in particular, we're going to look at the last row here, which is trying to meta-learn optimizers or algorithms, which is to say we want to be modifying the way that our weights get updated from time step to time step. The approach to this, I think, not only has its appeal in looking for the ultimate target, but maybe overcomes also a challenge with the building block approach, which is that we have all of these hundreds or thousands of really beautiful tricks and heuristics and approaches for neural networks, but getting them all to play nicely together and to build them into some very complex Rube Goldberg machine is in itself an enormous challenge. Where if we're simply asking the system to find the components or strategies that play well together, hopefully the integration is done for us at the same time. And I know that this is a very lofty and hand-wavy goal, but at least we have one existence proof of a meta-optimizer wrapping around a learning process, which is of course the evolutionary process that gave us human-level intelligence to begin with. So the approach that we're going to rely on quite a bit in this pursuit is the meta-learning approach from the Berkeley AI lab, particularly work from Chelsea Finn. So this work comes in the context of few-shot learning, where we're trying to find good initializations that allow us to quickly adapt towards any number of some independent tasks that we might be faced with in the future. The way that the meta-learning approach that we build off of, which is called MAML, the way that this works is it looks at the trajectories along each of the different tasks that we might ultimately be interested in, and takes gradients back through time to ask what initial weights would be most optimal to efficiently and effectively get to the ideal parameters that we would want for each of those tasks. Aside from the idea of actually doing backprop through time, a related idea of just looking at the final weights to try and choose our initial weights is also very successful. That's the reptile approach. So what we deal with is a related but slightly different problem when we think about online continual learning, in that we're not necessarily thinking about treating lots of different tasks independently, but we're thinking about how one task that we've learned affects the tasks that come before it. So we're looking at sequences, at trajectories through many different waypoints, which add in complexity over time, of course, but also the fact that we're likely to get overwriting as the direction of these caricature learning trajectories diverge from one another. So the application of mammal-style meta-learning to continual learning problems isn't something new from us. And concurrently with our work beginning on this, Martha White's group at Alberta put out a really fantastic paper that used a mammal-style meta-learning in a continual learning framework. We absolutely fell in love with this paper and adjusted much of our experiments to try and take advantage of a lot of the advantages of the approach that they put forth, as well as to try and test on very similar problems and domains, so that we could have good comparisons and a good starting point. So this work is absolutely inspirational for us, and I'll mention kind of again and again that the implementation I'm going to talk about in this particular work is based as much as possible on the work from Javid and White at NeurIPS last year. So the meta-learning approach I'll get to in a second, but one of the other key innovations that they put forward in this paper was the idea of separating which parts of the network are meta-learned or are fine-tuned on specific tasks as they're encountered. So the idea of meta-learning representations is that we know some features of representations are especially helpful for avoiding catastrophic forgetting, like having representations that are sparse and disjoint. And so taking the representation of this network, which is for them the convolutional layers only, and using a mammal-style initial weight learning to only learn these representation parameters in an outer loop of meta-learning is a very nice complement to then learning task-specific parameters in our task-specific task learning network in red that then use those features to adapt to new tasks as they come up in the continual learning framework. So this is a fantastic approach to continual learning, but suffers from what we think is one flaw that we're going to try and overcome in this work. And that's that the task learning network is still very much open to overwriting from SGD during each of the task learning sequences. So as we've seen before, the representations are put forth at meta-learning, but when learning on each task, the red part of the network, the task learning network, is wide open to changes. And depending on how the network is structured, it could be that much of this ends up overwriting previously learned behaviors or the way that we combine previously learned features. This is especially true as we scale these systems larger and larger and end up having more and more shared features between tasks just due to scalability. So our approach is very much related to this, but we introduce a new approach that we call modulated meta-learning, or A Neuromodulated Meta-Learning Algorithm, to be specific, which we call ANML. So ANML builds on mammal and reptile and OML. And what we do is we take the idea of having meta-learned weights and fine-tuned weights, but break the meta-learned section into this neuromodulatory network. You can think of kind of like a teacher or a regulator that is looking at the context that the prediction network is working within and suggests certain features or certain subsets of the network that should be on or off in that specific context. So in that sense, we're not so much creating features that we think will be robust, but actually going in and affecting the predictions that are made and the updates that are made during backprop. we do this through a gating function on the features before they get to our final classification layer. I'll go into more detail on this in just a moment. I'll just, at a very hand-wavy level, say that this is roughly inspired by neuromodulatory processes in the brain. Not so much in specific functions or chemicals, but more broadly that there exist processes, for example, chemical neurotransmitters that affect the bioelectric signals that we think of typically modeling with artificial neural networks. And that the relationship between both of these learned functions of when to release neurotransmitters and when to produce electric spikes are very nonlinear, but very coupled. And that's kind of the inspiration that we take in building our neuromodulatory network. So the way that this plays out in this particular work is that given some input feature, we would feed it into some neural network. And traditionally, we would just pass information forward through the layers of this network. Instead, we also pass that information through this auxiliary sidecar network that you saw before. This is itself a full multi-layer neural network, but for cartoon purposes, we'll just depict it as a little black box. And that black box function tells the original network where it should, what features it should pay attention to and which ones it shouldn't. So for any particular instance and any particular input image, it'll say, you should pay more attention to, for example, features 2, 4, and 5, and not so much 1 and 3. I've depicted this as a binary mask, but this is a real valued element-wise multiplication of a gating mask on just this particular layer. We chose to do this particular layer because it not only reduces the number of parameters, but is, I think, a good first foray into this approach where we can directly modulate what features are important for prediction during deployment of the network. But because we're shutting off the activation of certain nodes, we also downregulate information that's passed backwards during the backwards pass. So presumably we're only allowing learning in subsets of the network during training. Now I've said that we've just focused on this one layer where we can turn on and off some nodes in some contexts. And when we see different images, this function will choose to turn on and off certain nodes. But of course, this is just one particular instantiation. And we have ongoing work that's looking at regulating multiple layers or regulating edges instead of nodes. And I'll just kind of say at a very hand-wavy level that this approach is fairly general to the particular instantiation that we choose here. The idea of selective perception is nice because it changes the way that we behave in real time, but selective plasticity is also nice for consolidating learning, hopefully within specific encapsulated submodules within the network. Following the OML paper, we will train this network on a few-shot learning dataset, the Omniglot dataset, because of its vast number of classes, and we'll treat each task here as examples from a single letter within one of these alphabets, so that we can have hundreds or thousands of different quote-unquote tasks. Each of those alphabets has at least 20 instances, so we'll treat 15 of those as training sequences for that task, and 5 of them will hold out later to do tests on post-training. So I'll walk you through a simplified schematic of how this algorithm works. And I'll pause here and there to point out some inaccuracies of the cartoon here, but I hope that this is more informative in the simplified version. So the basic idea is that we train on a given task, and then immediately continue training on multiple tasks in this long online continual sequential fashion. Now, each of these blocks is itself a sequence of updates within that task. So like I said, that we see many highly correlated updates at small temporal scales in our lives. Instead of doing one or multiple batch updates on the 15 examples of this class here, what we're actually going to do is do true stochastic gradient descent, and do 15 updates on a batch of just a single image here, to hopefully provide a toy example that has lots of forgetting as we do many updates on new instances. For now, I'll hide the details of that for the simplicity of the diagram, but remember that as we go through. So after we've gone through one or more tasks, we'll perform a meta update that considers multiple of these task learning sequences, or I should say considers a sequence that includes learning on multiple tasks. And we'll ask again for exactly what we want in the meta-learning system, which is to learn the tasks without forgetting. And we'll use this meta update to obviously update our meta parameters. What that means here in our case is that we'll be using the meta update to update the weights of our neuromodulatory network, while contradictorily to this, the prediction learning network is trained on the sequence of data that it sees within each task. So here's a kind of the first example of multi-scale, temporal scales of learning. In that we have fast updates to the model, and then slower updates to the neuromodulatory Metalearn network. The loss for this Metalearn network is taken almost directly from the OML paper, which they call the online aware meta-learning loss. And this function, intuitively, you can think of this as going through a sequence and testing not only on the examples of the sequence that you've just seen, but on examples from prior tasks. In the paper, Javid and White take a slightly different approach to this, and instead have a disjoint remember set that are a specific set of tasks that we're specifically supposed to remember while we're training on other tasks. This is a simplification, perhaps, but helps quite a bit with the computational burden of taking gradients through very long trajectories, and turns out to work quite well. I see a note in the comments about this being related to attention layers, and yes, that's absolutely true. So there's many approaches that have a similar framing as this neuromodulatory layer. Attention is certainly one of them. The gating layers in gated mixture of experts come from a similar inspiration as well. So we're certainly not reinventing the wheel here. But I think that what's interesting here is the way that we apply meta-learning to this approach, which is that we take our meta update from that training and remember set, and we use that to update our neuromodulatory network at the next next sequence, the next task, such that hopefully we have a neuromodulatory network that's better at knowing where to turn on and off its gating throughout the training sequence. And of course, we'll repeat this approach for many meta updates until hopefully by the end we have a neuromodulatory network that is fairly good at deciding what features to turn on or off in a given context. But by the end of this, you'll see that the potential tasks that we have to remember are far more than the tasks that or the size of the validation set, which in our case, again, borrowing from the OML paper, we have a remember set of just 64 images. So this will be randomly sampled from the remember set. So to evaluate the efficacy of our neuromodulatory network, what we'll end up doing is testing it on a sequence of brand new unseen tasks. So while we called the training of the neuromodulatory network our meta training phase, we'll similarly call this meta testing. So this is a brand new sequence of K held out classes, each of which we again have 15 instances of that are strung back to back. And like I motivated our metric at the very beginning here, after the end of this sequence, we're gonna ask what the average performance is on all tasks within our sequence, and specifically on the held out instances in the generalization sets of each of those tasks. So that will be our meta testing performance. Now we can think of assessing this metric on different algorithms and also different lengths of sequential learning. So for example here, we'll show the average accuracy across a sequence of 10 tasks, plotted here at the very left of this curve. But we'll also expand this to ask how performance scales as the sequences that we train on become longer and longer, all the way up to sequences of 600 tasks. We cut off here just because we run out of omniglot images, but hopefully future work will show this on longer sets too. But again, treating these as finite sequences, after 600 or after 10 or 50, we'll go back and test how well the model can perform on all previously seen tasks during this meta testing phase. So starting with a straw man of traditional deep neural network trained from scratch, we see that after introducing sequences of online learning for just 50 or 100 tasks, catastrophic forgetting has set in, and we're able to remember virtually nothing outside of the last class that we've just seen, with performance asymptotically approaching zero. This isn't quite fair to compare to our proposed meta training and meta testing approach, because obviously meta training has far more compute and data than just training a network from scratch at meta test time. So we use that same amount of compute and data to pre-train the features of a neural network, as you would traditionally do in transfer learning. And these models have features that are more useful for providing high accuracy and hopefully disjoint representations between classes that help a little bit with catastrophic forgetting, but as we see for longer sequences, we still forget catastrophically and have performance approaching zero across those 600 tasks. Now, the online meta-learning paper explicitly rewarded the model for avoiding forgetting, and we see does much better, having some remembering of all classes, or at least more than just the final few classes at the end of our sequence of 600 continual 600 sequence of classes here. And a version of OML that we also introduced in this paper that came about through our many runs of trying to make sure that we were controlling for all possible points of variation, showed that actually if we took one of the fine-tuning layers and moved it into the Metalearn network, we end up with better performance on longer sequences. We can hardly blame the authors of OML for not noticing this, since they cut off their training sequences at 200 classes. So there was hardly the advantage that we see here for longer sequences with our improved version of OML. But lo and behold, the ANML approach of having this dedicated neuromodulatory network that gates or attends to the features ends up showing significantly better performance than any of these approaches. And I was totally amazed to see this, that it has, on average, mid-60s accuracy over sequences of 600 tasks, which is to say on some images that it hasn't seen for almost 9,000 updates. The question that was still left for me, though, was just how good this was. In some contexts, mid-60s would be quite good, and in others it would be quite bad. So to try and investigate what the ceiling is here, we also trained a quote-unquote oracle version of this, where we took the same models at the beginning of meta test time, but instead of showing them these sequential trajectories, we took all of that data and shuffled it IID to feed the network data that hopefully didn't have this sequential dependency, and thus hopefully didn't have any catastrophic forgetting. So there are many other reasons why we would have errors in this network, like the idea of taking one pass through a long trajectory of sequences. Even in the IID fashion here, we just pass one epoch of these shuffled classes through the network. So limited training time and potentially interference between tasks or model capacity means that we get low 70% for the quote unquote catastrophic forgetting free oracle version of ANML. But I was really impressed by this plot when Sean showed it to me, because the drop between the quote unquote catastrophic forgetting free or minimal catastrophic forgetting version of the IID oracle relative to the continual learning version of ANML is a much smaller difference than any of the other approaches. So while I certainly don't want to go so far as to say that we have or maybe even that we've come close to solving catastrophic forgetting, it appears as though, at least in this instance, we've drastically reduced the effect of catastrophic forgetting on these very long sequences of sequential tasks. To round out these results, I'll also note that while the last plots showed the error on the held out generalization set for each of those tasks, if we're thinking about what ceilings we might have, we can also assess how well the models remembered the exact training instances they were shown during this sequence of 600 classes. And as you would expect, performance increases across the board, but animal here has a mid 90% memorization of the training instances it's seen, even though it hasn't seen some of those for thousands of SGD updates, which again gives us some promise that we have an approach that can help mitigate catastrophic forgetting in this setting. So I just have a couple minutes left, and there are all sorts of open questions that come up based off of these results and how and why they work. One that we quickly tried to explore was the idea that what you really want for catastrophic forgetting is sparse and disjoint representations. The OML paper really nicely found that their meta-learning approach outperformed a control algorithm that specifically incentivized sparse representations instead of incentivizing less forgetting. So again, playing off of this meta-learning ask what you really want idea, we see here that the post neuromodulatory activations in our network are very sparse and quite disjoint. You see on the right that the mean activation is pretty uniform, meaning that we're using different neurons for different tasks, despite the pre-modulated activations in the top row being not all that sparse. In fact, much less sparse than I would have expected. We also concurrently and inspired by some work looking at how meta-learning clusters representations from Tom Goldstein's group in Maryland did some analysis looking at the clustering of the representation layer here, which is the one that we're modulating. This finding holds for our whole 600 set of 600 classes, but I'm just showing 10 randomly chosen classes for the sake of visualization. When we see our pre-modulation layer has some patterning in how it separates these classes in a t-SNE projection. But we see that adding in the effective modulation really nicely and really tightly separates these classes, which I was not expecting to see kind of this level of separability in this network, especially given that the OML activations, which still did quite well from a catastrophic forgetting perspective, don't seem to show this type of separability quite so well. Which I was kind of surprised by. I would think that that specifically learning just the features and just the representation layer, you would need that to be kind of very disjoint and sparse and cluster quite well. So I think there's lots and lots of more work to do investigating how and why this process helps to mitigate forgetting. So just to wrap up as I finish the time here. We've shown that selective plasticity through context-dependent gating or meta-learned attention helps protect against catastrophic forgetting. I'm hopeful that as we apply this towards meta-loss functions that ask for things other than catastrophic forgetting, like maybe forward transfer during sequential learning, we'll see similar good news there, but that's a work in progress. We've seen that the meta-learning is indeed a very powerful tool for learning these gating and attention functions. And it allows us to very nicely take long sequences of tasks and do reasoning and learning over them. Again, what I've showed today is just one particular implementation of this, and I think that there's many other meta-learning setups that are similar to our particular instantiation that we're exploring now. In particular, our ANML algorithm, we showed on sequences of 600 tasks, which are some of the longest I've seen in the literature, and I'm very optimistic about this, but certainly want to push this further to longer sequences with more distribution shift than just looking at different instances of the same data set. Really looking at transfer between data sets at meta testing is where we want to be going, what we're actively working on now. And just kind of more generally to wrap up, this idea of optimizing for what we really want, which is in this case, reduction in forgetting, it has shown time and time again, including here, to outperform the traditional building block approach of thinking really hard about the way or the features of a solution that you think the network should be taking and incentivizing directly for that solution. By allowing meta-learning to explore the space of all solutions, we do better than those that are, at least in some particular subset of hand-coded features, better than those hand-coded heuristics. So there's lots more work to be done. I'm happy to talk about that or any of the past work in the Q&A, but I'll wrap up just by saying a huge thanks again to all of the team of really fantastic collaborators, all of which I couldn't have done this work without. And also to our funding source for this particular paper, the DARPA Lifelong Machines program. There's a lot of really fantastic work coming out of that, and I'd encourage you to check it out too. So thanks so much for your attention and your curiosity today, and I'm happy to open it up for Q&A.
Thanks so much, Nick. Really fantastic talk. And now, so now is the time when I normally, if we were in real life, I would say thanks to the sponsors for buying the beer and pizzas, but obviously we're not doing that. But I do need to thank the sponsors anyway. So thanks to ManAHL, who many of you know already, are a hedge fund who are doing lots of interesting stuff with machine learning, and also the company where I work, Evolution AI. We make products for data extraction from images of documents like PDFs and scans. Great, so now I'd like to introduce you to Brandon Amos, who's going to be facilitating the Q&A section. We were slightly late starting, so if everyone's okay with it, I'm going to extend our time by a little bit. Brandon and Nick, are you okay to hang on for another 10 minutes after our scheduled time? If you're okay with it. Cool.
It's good with me.
Great.
Sounds good to me.
Perfect. Great. So Brandon, over to you. I just need to tell everyone to keep putting your questions into the Q&A and raise your hand if you want to ask a question yourself, and I'm going to unmute you. Otherwise, over to Brandon. Thank you.
All right. Yeah. Hello, everyone. I'm Brandon. I'm a research scientist at Facebook AI and work generally on optimization and machine learning and controls and reinforcement learning. Yeah, thanks, Nick, for the great talk. I'm curious to go into quite a few different topics related to it to kind of hear more about how you're thinking about problems in this space. This is the first question that we got. I think it's really thought-provoking and kind of touches on like this broader issue on what we need to do in machine learning when our data changes by like something massive, like how ML should deal with changes caused by COVID-19 or other kinds of like critical events that just totally change the rest of the measurements that your system ever gets. And I guess it would be curious to hear your thoughts on that, but also more generally, when you think that using meta-learning to look at, say, like the catastrophic forgetting case like makes sense, and maybe when it doesn't make sense, because it seems like there are some tasks or settings that make it really hard to run a lot of kind of like trials or to have like a lot of subtasks where like now in the world, like after something happens, like you don't get to go back and like try something else from scratch. So I'd be also curious in hearing what you think about that.
Yeah, those are both really interesting questions. I certainly don't have any specific solutions about how we deal with COVID. I think we're all struggling with that. But the kind of general question about how do you deal with big unforeseen obstacles, I think actually fits really nicely into the philosophy here, if not the particular results from our kind of limited toy experiments. But the idea that, you know, instead of thinking of building a set of features or a knowledge base that encapsulates all of the things that you might one day see, the idea of focusing on the learning processes themselves and how learning one thing affects learning on something else, regardless of what the particular nature of those things are, I think is really appealing for the cases where you don't know what you're going to expect to see, or when you actually do know that you expect to see something you've never seen before. And I think that kind of high level idea is just so appealing to me. You're certainly right that in COVID and in many other cases, the idea of having you know, many tasks to go back to is a constraint that may not be realistic. I think that there are opportunities to expand kind of the naive version of having to sample instances from everything you've seen before, to try and mitigate forgetting, to think about, you know, really salient events or things that are recently important or recently learned. I can imagine, just from a scalability perspective, that this is something that is relevant to the way that we actually learn. But I'm certainly overstepping my area of expertise there. But in general, actually, I think that the idea of having lots of small little data sets and not these kind of research curated huge, you know, ImageNet scale endeavors actually is much more realistic. That I one of the great things about the university here in Vermont is we have a big med center next door, and no one there has, you know, huge data on any one particular disease or pathology, but everyone has related data sets that are small on all of their separate things. So the idea of teaching a model in a few-shot learning way from lots of instances of small data, I think is really appealing generally too.
Nick, I had a question for you, actually. Based on your plot of the Oracle results, I don't know if it's easy for you to...
Sure.
I think you were showing that the animal in the Oracle setting, in the IID setting, is performing a lot better than the kind of deep learning baselines. Yeah, this one. I guess the question is, you know, this is like a few shot setting, I guess. So there's only, I think, 15 Cheney examples each time. So how much of your gain is due to having some kind of mammal type architecture or approach, as opposed to your neuromodulatory network? I mean, how you know, did you try doing things like having a randomly initialized modulatory network, and, you know, some kind of ablation study of that?
Yeah, we have that sort of work ongoing now, and I don't want to speak before I have good results there. But yeah, the particular importance of each of these different parts of the network and on the specific implementation of each of them is a really interesting line of work that we're interested in moving forward. I would also say one of the figures we had in the supplement of the paper is looking at in the Oracle setting, we can relax the assumption that we just have an online trajectory that we see once as it flies by us. And we can go back and do multiple epochs like we do in regular deep learning. And it turns out that the meta-learned approaches do improve but the kind of trained from scratch or pre-trained approaches also improve by much more. Maybe this is because they start from kind of such an abysmally poor level. But I think that it's interesting that having multiple passes through the network affects these different algorithms separately, and I still haven't seen an example of training enough with a model built from scratch where it outperforms our meta-learned approaches. But I would expect that would kind of eventually happen, just because you're training on the thing that you really care about.
Thank you. Actually, on the subject of epochs, I saw that in the paper that for the meta-train training, you used 20 epochs, but then for meta-test training, you were using 1 epoch. I kind of just wondered why that was.
I think there might be either a slight confusion or maybe a writing error on our case. But there's the number of instances, the number of images for each class, and then the number of epochs through the entire data set. And so in the meta training, the 20 is for the number of examples in a row that we show of each particular task.
Right.
And we do end up going through the whole data set multiple times, just because our meta learning time is longer than the amount of data that we happen to have in Omniglot. But we've done some studies modifying the amount of meta training that we do, and I'm very surprised at how robust it is to less and less meta training data.
Cool. Brandon, do you have a question, or should we go to a QA from the audience?
Yeah, something else I'm curious about, kind of more kind of like as a vision and the direction that this work is going. I think the idea of meta learning, if like the neuromodulatory unit is like, it seems like you can combine this with some of the other approaches to helping to avoid catastrophic forgetting. So I'm curious if you've thought about other ways that you can use meta learning in like the context of online learning, like these approaches that, for example, maybe try to keep some of the past data around, or try to keep some of like the memories of the past experiences around, so that they can use like these key moments during like the history to inform how to make a decision at the present moment. It seems like something like this can like fit kind of nicely into the meta learning setting as well. So have you thought about going in this direction of meta learning more components and inside of the module, or do you think that it's what do you think of that direction? Yeah,
that's a great insight. So there's kind of these broad categories and approaches to catastrophic forgetting. And two of the ones you mentioned are ours, which is kind of more of a selective plasticity, kind of a protection of weights, and another being more of a replay style approach. And there's some nice hybrids already in between those. But yeah, generally, we haven't haven't run as many of these controls as we'd like so far. But I think I see lots of potential for a synergistic relationship between approaches in different bins that some of the more replay style methods, like you mentioned, I think would play really nicely here. Whereas other selective plasticity approaches like elastic weight consolidation may have advantages, but I could see lots of interference between different approaches to trying to do the same thing too. So in short, yes and no, but with a optimistic yes.
I see. Yes, great. Makes a lot of sense that you can kind of leverage the knowledge from very concrete examples in the past, along with kind of leveraging the knowledge of what features to look at for this specific example you're trying, or for the specific task you're solving. Something else I'm curious about on the application side is kind of is on the going into the reinforcement learning and control space, because it seems like if you're designing agents that need to interact with the world over some long period of time, like the examples that you gave of riding a bike and then going and trying to learn how to do other things and then maybe going back to riding the bike, it seems like it's the perfect application of kind of of needing a model that can't catastrophically forget its past experiences. So I'm curious if you've been thinking about pushing into this more kind of RL direction for in this space as well.
Yeah, you're right. This is absolutely the perfect sandbox for it, I think. It's a direction we're actively moving towards, but I don't have any results to share right now. I would say that we're cautiously optimistic, but very much cautious about how the kind of noisier signals of RL will play with the longer temporal dependencies and sensitivity to gradients that we might see in meta-learning. So I think that what I'm expecting and maybe hoping for is to see some promising results at first, but I think that we might need to pull in some tricks or come up with some tricks about stabilizing gradients that will be needed before this really takes off.
I can see a few good questions in the QA. Also, I can see some hands raised. Guys, if you raise your hands, could you also type your question into the QA and then we'll select your question. Felipe, would you like to ask your question yourself? Just raise your hand if you would. Otherwise, we can ask it for you. Okay, I'm gonna read Felipe's question out. It says, excellent talk and impressive results for multiple digit recognition tasks, a step towards general purpose AI. How do you think this meta-learning approach would work with higher inter-task variety?
Yeah, great question, Felipe, and thanks for the kind words. Yeah, so this is kind of related to the point I made, I think, to Brandon about looking at meta transfer to new domains or new data sets. And that's kind of a abrupt kind of one-time thing where we go from one distribution to an entirely different distribution, which is challenging, and I can say we're still exploring, but it seems like there's a lot of potential there. The question also seems to be getting at the inner task variety kind of within each of those data sets or distributions too. And I think that's a really important point. We don't have very satisfying metrics for describing that, that are kind of agnostic to a particular network, which I wish we did. But at least the way I conceptualize it, I think that's kind of critically important when we're trying to learn how to learn a set of diverse tasks. The more diversity that we have in our training set or our meta training set, especially relative to the amount of diversity we expect to see at deployment time, is obviously going to be really crucial. And exploring how we can how our results depend on what data set we use for meta training, or a direction that we're going is to use multiple data sets for meta training. I think it's absolutely an area worth exploring.
Nick, I saw in the OML paper that they tested on Omniglot and also this other data set called incremental sine waves. Do you have some results on that data set too?
Yeah, we haven't tried the incremental sine waves in a I think an updated version of the OML paper. They also looked at mini ImageNet, and we've been looking at ImageNet and CFAR, and so far the results are early, and we're still analyzing them, but it looks promising.
Cool. Brandon, do you want to select a question from the audience, or do you want to go with one of yours?
Yeah. I'm curious to hear this one by this last one by sorry for the pronunciation, Kai Arukumaran. If you would like to ask that.
Yeah, Kai wants to ask his question.
Live.
You're unmuted, Kai. Oh, you should be. Yeah, you are.
Hi. Yeah. Cool. Thanks for the great talk and work. So I'd just like to ask, what sort of ideas do you have towards improving the scalability of this? So like, would you be using hypernetworks maybe to kind of operate on a larger part of the prediction or task network, or operate on a sort of latent space? So maybe going with Brandon's question, like thinking about generative replay methods, like would you be able to use latent spaces to maybe improve the scalability of ANML?
Yeah, great question. That's, I think, one of the big open questions here is what's the way to make this the most scalable? And our implementation now is kind of purposely very naive. So certainly the approaches you suggest are great ones. One that we kind of have begun to explore a little bit is that one of our co-authors here, Ken Stanley, is the pioneer of the compositional pattern producing networks, which are kind of generative spatial encodings that give a really nice indirect encoding for high dimensional spatial networks. And his approach, HyperNeat, is one of the most widely used in the evolutionary optimization space. So that's one direction we've been going in looking at indirect and generative encodings from mapping our neuromodulatory signals onto some huge network. I can also say that the preliminary results that we have, even using our really naive kind of direct one-to-one encoding of modulatory outputs into the prediction network, has scaled much better than I thought it would. I'm always kind of impressed at just how well backprop does at giving important gradients through these huge layers and widely distributed parameters. I'm sure that there are much better ways to go about it than the ones that we're exploring right now. But even kind of the simplest case scenario seems to be working better than I thought it would.
Kai, do you want to follow up, or you good? Okay.
Thanks, Kai.
Thanks, Kai. Brandon?
Something that also seems kind of remarkable is some of the lengths of the tasks that you're considering, like having it's like 600 steps. I'm curious if that's kind of hard to do, or if there's any stability issues that you faced while getting that to work. Because usually people, when they talk about meta-learning, they're thinking more in the range of only doing a few steps or maybe 10 steps to update their model, rather than going through hundreds or potentially, I think in your case, thousands of steps. So it's somewhat remarkable that you were able to get this to work so well.
Yeah, and that was a little side note that I glanced over quickly and should have put more lip service to, that we 100% cheat our way around that and don't actually go through backprop through time over 9,000 steps, but really use this remember set from the OML paper, so that we only have to go through kind of single inner loops of our 15 or 20 instances, and then use the remember set, kind of like a replay buffer, like you mentioned, to assess how much forgetting there might have been had we looked at all of the other prior tasks, or or done backprop through those. I think that we're losing a little bit of fidelity by not actually doing full backprop through time through multiple tasks. But so far it works pretty well. I'm interested in scaling this from kind of the very simplified version of just one task, but and not going all the way to the 9,000, but saying, you know, if we were to do backprop through time just through a few of those tasks, how does that fall off as the number gets decreased from that absurdly long 9,000?
Yes, I see. That makes sense.
So guys, we're well over time now. I'm just going to ask one last question, which is from someone from the audience, which is DA. DA is asking, is there code available? So just generally speaking, Nick, how would people start to play with this model and get involved? Yeah,
great question. There is code available. It's linked in the paper, which you can find on arXiv. I'll note right now that this is built off of the OML code base, and Kareem just pushed a major refactoring of his code a few weeks ago. So we're going through that and addressing some of the bug fixes that he found. So I might encourage you to wait another week or two while we make sure everything's still working well. But before you play on with it, but it's there for you to check out, and I would love to get feedback or try and help if you're trying to spin up some experiments of your own around this.
Fantastic. Well, thanks so much, Nick. Really appreciate that. Thank you, Brandon, for facilitating the discussion. Sorry we didn't get to all the questions from the audience. We just ran out of time, but thanks everyone for joining, and we'll see you next time.
Thanks, everyone.